Kendra is in the house. Jasmine is in the house. From hither and yon.
I think that they,
All righty. Well, welcome to my last show before the weekend starts. So we're going to finish up our final case study 10 today. I don't think it'll take the full period, but who knows, maybe we'll get into some conversations and you guys will drag it out. I don't know. I know you'll be riveted by all this allometry we're going to be dealing with today. Anyway, so we'll finish that up today. Then next week, I have 2 lectures that I will provide some content for. I honestly don't know what it's going to be yet, but it's something that I will think about during the break, and I will have something for you. It'll probably just be a couple of lectures. I'll pick another physiology topic to deal with and come in and just get you all excited about it. And then on Friday, remember, I will be out of town on Friday, so you will be working on your projects during your time on Friday. Then for our final week, we will be doing oral reports all week. So all 3 lectures and two of you during the first part of lab on Tuesday, and then we'll be done, except for finals week. So that's kind of the schedule. You guys have any questions before I get going? You all look like you're just like ready to be done for this week. Is that pretty true? Yeah. You want the truth be told, so I'm ready to so be done too. Okay. And Kendra and Jasmine are already done, so they're sitting in a cozy place.
yeah.
Okie dokie. I know it seems like ancient history, but we were talking about this nifty study in which the authors were looking at 2 species of fly, a mosquito and a regular fly, a dung fly. And maybe I'm gonna make your brains work. Refresh my memory. What was the premise of this study? What was the point?
Investigate energetic mechanisms that might select against the larger body size.
That's correct. So they were looking to see if there was a scenario in which the smaller body size might be favored by excuse me, selection. And what sort of a scenario did they propose where that might work? And you Zoomers, feel free to chime in. Did they feel it would only work when aliens invaded the planet?
Mhm.
Okay, Whitney agrees with that. was an energetic reason
Food limited environment.
in food limited environments. And why? Why did they think that that might be a scenario which may favor a smaller body size?
It's because larger animals need more food to support their higher metabolic rate.
Okay, that is a portion of the answer. So when we remember the 3/4 power rule? Tell me about the 3/4 power rule. Abby, come on, tell me about the 3/4 power.
I wrote down that it relates to scaling.
This is true. It is a scaling exponent.
I don't remember why it's 3/4.
True or false? The 3/4 power rule represents isoallometry.
Oh,
Why is that false?
because the slope is less than 1.
Okay, it's less than 1, which makes it
Hypoallometric.
hypoallometric. Okay, well, we're getting somewhere. So the 3/4 power rule suggests that something that you are relating to body size, in this particular case, it's energy expenditure, metabolic rate, is hypoallometric, which means what? What does that mean for large organisms relative to smaller organisms?
They're more efficient.
They are more efficient energetically, okay? This is related to things such as surface to volume ratio, that kind of stuff. Now, how does that relate to the allometry of activity? This was an important point that the authors made. I'm getting us set up to go and discuss all of this stuff here.
Larger animals need more absolute energy than
Well,
smaller animals.
that's true. That doesn't make it any less hypoallometric because mass specifically, they would still have lower energy expenditure. But and just in terms of absolute energy that they need, they do need more. But what was the statement that the authors made with regard to the exponents? The allometric exponents that are often associated with activity, such as flight.
Large individuals should deplete reserves faster than small individuals.
Okay, that's getting at the answer. That is a consequence of the answer. So if resting metabolic rate for a larger organism is, at least on a mass specific basis, lower than in a smaller organism, basically establishing the 3/4 power rule, which is hypoallometric. What did they say the allometric exponent might look like if you were to scale activity as a function of body size?
Maybe steeper.
Steeper. They said that it is often hyperallometric, which means what for the larger organism?
Should they deplete their energy source faster?
That they deplete their resources faster. So they are not more efficient. Larger organisms are not more efficient when they're spending energy on activity, or not necessarily more efficient when they're spending more energy on activity, which means they will deplete their energy resources more quickly. And I showed you a hypothetical or a theoretical model in the form of a graph where we looked. Goodness, why is it that black pens always disappear. So when we, okay, anyway, let's do it this way. Let's and show. I'm just going to show it to you, I guess. So this figure right here, okay, the top line up there, solid line, and you should remember the solid, the hatched, and the dotted because they'll use the same convention in data that we're going to look at in a second. So here we have energy reserves. They scale, and what they would argue is that the scaling of energy reserves, they would predict that it would be to the 3/4 power. It was one of their predictions. Okay, and they said that if the scaling of activity is hyperallometric, such that larger individuals it was going to cost them more to be active than it would smaller individuals. It would flatten. It would flatten the scaling of that, with regard to the depletion of the energy reserves. Okay, so that it would scale with a much shallower slope, because bigger critters were using up their energy reserves faster than smaller ones. Does that make sense?
Why wouldn't it be negative?
Well, it could be negative. It actually could be. But by flattening, it means it's not going to be as steep as the resting reserve slope would be. Okay? But it's going to flatten because on the heavy end, they're depleting much more quickly than on the lighter end. Okay, and if they deplete way faster, it could go negative. Okay, and in fact, when you look at their data, I think there'll be at least one example where that's the case. Okay, and so the reason why they think that activity in low food availability situations might select for smaller body size is because of this hyperallometry of activity. And so they are going to test these two species of flies in flight in 3 different food levels, really low, low, and high, to see if when food is restricted, whether the small critters do better. Okay, is that how you remember it? Sure. Okay. All right. Let's look at some data. All righty. Yasmin and Kendra, can you see my screen okay? Make sure I didn't screw it up. Are you even there?
Oh yeah, we can see it. Thank you.
All right, thank you. All right. Oh, that's not even the right. Okay. The wrong one. I will get there eventually. There we go. All right. All right, so what we're going to do now is we're going to walk through, if you remember when we finished up on whenever we did this last, so what was it, like Wednesday, or it was Friday, last Friday. We went through a series of 6 predictions that the authors made with regard to their data. So we're going to go through each one of those and see how their data supported their predictions. All right. So here are the graphs that they present here. They're using the same convention as in that hypothetical graph that I showed you a moment ago. So the solid line is always going to be the baseline reserves, okay, which they are going to predict are going to scale to the 3/4 power with body size. The hatched lines here represent unflown reserves, and the dotted line represents flown residual energy. All right. The ones we're going to look at the most here are going to be the dotted line and the solid line right here, the difference between those two. Okay. So they're going to look at each species of fly separately. We're going to start with the mosquito. And so for all three energy components, remember they looked at glycogen, sugars, and lipids. Okay, glycogen and lipids are storage forms. Sugars are things they can be storage forms, but they tend to use those. That's generally stuff that they are consuming directly as food. And then over here we have across in the rows, we have our low food, our not quite so low food, and our high food availability condition right here. And then on the y-axis, the left y-axis here, we have energy content. And this is basically the energy content of the flies, okay? How much energy is stored in their body. Okay, so first, for all three energy components, glycogen, sugar, and lipids, they generally, and whenever you see a scientist use the term generally, it means that it was a little messy. But they generally increased allometrically with body size for all the mosquitoes. So in other words, the larger you were, the more energy stores that you have. And they're speaking specifically with regard to the solid dark line here. And if you look at the solid dark line, you can see that they angle up in most cases. So that their prediction number one was supported. Okay. Individual energy content increased with food availability. So as sugar concentration went up, the amount of energy reserves a given individual had also went up. Now, the thing you got to be careful of when you're looking at these graphs right here is the axes are not identical. So when they talk about a slope down here being steeper than a slope here, even though it may look shallower, you got to understand that the axis here is double the axis of these two graphs. So that kind of plays a little optical trick on you. All right. But overall, when they looked across all of the different types of energy storage that these flies exhibited, as the sugar concentration went up, the amount of energy that they were storing internally was also going up. So prediction number two was supported. Prediction number three was also supported, although that was a pretty easy one to support. Baseline energy content was the highest condition in which they were measuring energy, and that's the solid dark line. Flown residual energy, in other words, the amount of energy that's left in the body after the flies exercise by flying, was the lowest, and that was the dotted line down here. So it's a difference between the solid black line and this dotted line right here. Okay, and then the hatched line, which is basically resting after they just, they weren't flying. They were just walking or, sitting on the surface someplace for a period of time. They had some intermediate value of energy storage. Okay, so prediction three was supported. Okay, now we get to where things vary a little bit from their predictions. So scaling exponents, okay, differed between the different types of energy storage. So remember, they predicted that energy storage should scale to the 3/4 power based on the 3/4 power rule, right? But they found that that was not the case. They differed between energy components and was closest to the 3/4 power rule for sugar. So just the middle column here. When we look at the baseline reserves, they were closest to scaling for the 3/4 power. And these sugar reserves probably were influenced a lot by what they were eating, because they're pretty, they are available pretty directly, and which may be influencing this. But if you look at the glycogen or the lipids, you see that there's quite a variation from the 3/4 power rule. So there is what that tells you. Oh, I'll let you tell me. What do you think? What does that tell you about what's going on with energy storage? Any thoughts? The authors made this prediction thinking that the proportion of your body that is dedicated to energy storage ought to scale to 3/4 power with your body size, because it's going to reflect your energetic need. But that didn't turn out to be the case. Glycogen and lipids, which are really more common types of long-term storage, clearly deviated from this. They did scale with size, but they deviated from the 3/4 power rule. Any thoughts about what that might mean? Silence. Should I just tell you? What this probably means is that there is something that influences energy storage beyond simply body size. And that will turn out to be the case. Okay, so in general, as food availability increase, so we go from 0.5% sugar to 10% sugar, okay? The scaling exponent got larger for glycogen and lipids, but not for sugar. So what this ought to be telling you is that there is something going on that's different with regard to glycogen and lipids. Something is going on that's different about them than about storage of simple sugars. Okay. Questions about this slide? So what we've done to this point is the authors have used some allometry here to identify some components of their ability to fuel their metabolic expenditures that is not just directly related to the size of the adult fly. Okay, and we'll find out what those things are in a bit. Okay, so their next prediction was the allometry between energy and body size flattened in the flown group. That's that dotted line right here, relative to baseline. Although they point out for the mosquitoes here, this was only a slight change for the lipids. So if you look in this column here, you don't see a huge flattening. And to be honest, this could be a little wishful thinking on their part by making this statement. But you definitely see that in sugars and glycogen. Okay, and they're using this to indicate greater energy expenditure in larger individuals during flight. So they're arguing that the allometry of flight activity has a steeper scaling exponent than the baseline energy storage does, or even the resting metabolism for that matter. So they would argue that this supports their prediction 4. Now, here's the caveat though. The flattening was driven more by differences in flown and unflown. So in other words, active versus inactive, as opposed to food availability. So they're admitting that food availability in and of itself really didn't drive this pattern. So this is the first finding that probably is working against their ability to demonstrate any sort of selection against large size. Okay. The lack of relation to food availability was in part due to a lack of difference at higher food availability, 10%, and they will address this a little bit later. Okay. And longer flights by larger females. So we have a sexually dimorphic difference in mosquitoes that they weren't expecting, which has kind of mucked up the works a little bit. All right. Any questions about this slide? Yeah.
Why do you think the glycogen for the 1% sugar would be steeper than the other two? Like, why wouldn't it follow a pattern like where it increases?
You know, it is a good question. And I guess what I would point out is look at the scatter in those points. I think there's a lot of variability. And you know, when I told you that they use a word generally, this is why they use the word generally, because there is an odd line that doesn't exactly fit the pattern the way that they do it. They don't actually address these resting values very much. They focus on the flight and baseline values. So I honestly don't know the answer to your question, other than it's just a matter, I think, of it reflects the variability in the data. Other questions? Okay, the dung flies get even worse. Yeah, I know. So we're going to go through the same 6 predictions on the dung fly. So dung flies, all 3 again, components increased allometrically with body size. So P1 is supported. We're looking at the solid line. You know, it's got a positive slope. It's higher for the big critters and lower for the small critters across the board, with the exception of this one right here, which I'm sure you picked up on, Whitney. That one right there. We got an explanation for that one. Individual energy content increased with sugar availability, so same as with the mosquitoes. P2 is supported. Baseline energy content was highest with flown residual energy being the lowest. So in other words, the solid line in theory here is higher than the dotted line, but the point that I want to make is that's not really clean for the dung flies. You look here, and they cross in the middle. So I'm sure the authors are kind of stretching this a little bit and reflecting mainly on the large group here. But if you look across all of the panels here, for the most part, that holds true. But it's not as clean as it was with the mosquitoes. In the case of the dung flies, none of the scaling exponents were close to the 3/4 power rule. So this is suggesting that these dung flies are behaving a little bit differently than the mosquitoes did. Now, one thing, I mean, if you look at the morphology of a dung fly, which really follows the morphology of a pretty typical fly, versus the morphology of a mosquito, they're actually quite a bit different, and that may have something to do with it. The scaling exponent did change with food availability, okay, for glycogen and lipids, but not sugar. So again, we see an influence of of food quality or food availability influencing the longer term storage products, glycogen and lipid, but not sugars. The sugars are pretty messy, actually. Okay. A systematic decrease in slope relating energy content to body size is only seen in low food availability. Okay, so in other words, if we look at the lowest food availability, and again, you got to pay attention to the axes here because the axes are not the same for all panels. The only place where it really tends to be flatter are going to be the lower food availabilities. Okay, where we see that the slope is shallower. Okay, and like the mosquitoes, the dung flies flew farther at higher sugar concentrations, 10%, but distance did not increase with body size, which is a difference from the mosquitoes. At least in the mosquito females, they flew farther. Okay. So, and I think that reflects I'll use the term messiness of these data because you don't see the same strong relationship between size and energy storage that you did in the mosquitoes. Okay. All right. Questions about this? Yeah.
How would it be possible for the flown, I'm kind of confused on how the dotted line would be higher than the.
You know, that is a really good question. And I think the best explanation for that is they've extended the lines beyond their points. So there are multiple ways you could look at this. One is you could maybe argue that there really is not a linear relationship there. And so you have nothing down here. So all of this really is not really useful. And this may be why, if we go back to their first three predictions, why they feel good about their first three predictions, because once you get, you know, when you're looking at something like this, it doesn't matter what the lines are doing here. It only matters what the lines are doing here, because that's where the organisms are. So clearly here, your baseline reserves are certainly higher than your flown residual energy, which, by the way, you can see has a negative slope here. Okay. And this one here perhaps is a little messier, but you know, it's hard to pick out real relationships in any of that because it's kind of like a cloud. I think the allometry associated with energy storage is just not as clean with these dung flies as it is with the mosquitoes. Other questions? Okay, so conclusions. Prediction one. Both the flies showed a positive relationship between energy reserves and body size. Okay, even though it was a little messier with the dung flies, the authors felt, well, so did the editors because they published the paper. They felt that that if you were larger, you had more energy reserves. Okay. Now here is what is likely making a lot of these allometric relationships messy. One of the things that they found was that both these flies have larval stages. And one of the things that they found was that the adults benefited from some carryover energy reserves from their larval stage. So anyway, the carryover over energy reserves, these are referred to as teneral reserves. They drove the variation from the 3/4 power rule in energy storage. So remember we talked about how the fact that that something other than just the body mass of the adults is dictating their energy storage. In this case, the fact that these individuals were getting some free energy from the larval stage. The larval stage would acquire the energy, and then as they metamorphed into the adults would retain those energy stores. So that added to the energy stores of some of these flies. And so that caused a variation from the 3/4 power rule. And what they also found was this meant lipids in the mosquitoes, which is probably why the regressions on the mosquitoes are so much cleaner than the dung flies. And then sugars and primarily glycogen in the dung flies. Prediction 2, higher food availability led to greater energy reserves. Okay, generally that was correct. Again, a little messier in the dung flies. 3, energy reserves during flight were depleted more quickly than for individuals at rest. So this is the one conclusion that involves that hatch fly. Okay, and so this is their argument for probably a hyperallometric relationship associated with the cost of flight and body size. Prediction 4, the allometry between energy reserves and body size tended to become flatter in active, flown and unflown, relative to baseline, which is pretty much true. It didn't have as steep a slope because the energy costs were higher. Okay, and the authors suggested this supported activity metabolic rate scaling more steeply than resting metabolic rate. I think they made a good case for that. Agree? Okay, flatter reserve scaling as food supply decreased indicated food limitation. Only occurred for glycogen and lipidism in mosquitoes, because remember, we didn't see a change in slope in sugars, and in the high sugar concentration for dung flies. So you remember how energy reserves were kind of flat in sugar for the dung flies? And what the authors are thinking is that 10% may have been too high for the dung flies, and they may have had some issues consuming and digesting it. They never really say specifically why they think that, but that was one of their suggestions as to what could be driving that result. Okay, and predictions 5 and 6, the positive relationship between body size and flying distance suggests that larger flies have greater flying capacity. Okay, this was one of their predictions. They would have more onboard energy storage, so they would be able to fly farther. Okay, this was largely driven, however, by the higher fuel reserves of larger individuals, and that's a result of those teneral reserves that we talked about a few moments ago. If you were larger, had a larger larva perhaps, you got to carry some extra with you, and what they will conclude in a moment is that they think that this compensates for being larger in size. They did say that data for the mosquito did support this idea that larger individuals could be limited by greater absolute energy demand at low, and when energy availability is low. But as you will see in a moment, our final conclusion really shows no selective pressure against larger individuals in this case. Okay, questions? Doing okay? All right, last slide. So the authors suggest that their data document both greater baseline energy reserves as well as greater absolute and relative energy demands for larger flies. So That part of what they suggested is correct. You know, you're bigger, it costs you more to be active when you're bigger than it does if you're smaller, okay? But by the same token, you also store more energy. And since they identified that larger individuals actually were able to up their energy stores even more because of these temporal reserves, that helped them out. So the greater energy demand of larger size appears to be compensated for by the greater baseline as well as the increase in temporal reserves, which is something the small flies don't have. So, so the scaling of the onboard energy stores is going to be steeper than it will than a 3/4 power. So when all is said and done, no evidence was found that that selection was favoring small body size, even in an energy limiting scenario. Questions? So if you're one who likes to do theoretical kinds of analysis and modeling, allometry is just a cool tool. You notice how that runs? A cool tool. Okay.
Could you go back to the last slide?
Are you still writing? See, if you use your thumbs, you would do it faster, right?
Hold my pen with holding myself.
All you youngsters and those thumbs just thumb type. So that is a wrap for case study 10. Or case study 7. Sorry. It's topic 10 on my list of things. Questions? If not, then you are free to begin Thanksgiving. Piece I feel sorry. Unless you have another class after this, then I can't go. We are still free to begin Thanksgiving. Any questions from the Zoom gallery?
Nope, thank you.
You're welcome. Emily, can I turn off this slide now?
I guess.
Oh, you guess? Okay.
If you must.
If I must. You're welcome. You too.
You going around?